Welcome to the 17th lecture video for Physics 4A. We continue our consideration of rigid body motion, including rotation. In the last lecture, we introduced the torque and rotational kinematics, and we have just one more thing we need to introduce before we can start considering all possible rigid body dynamics. So, we start with the rotational inertia by considering the form of rotational analog to mass, that is, inertia, that would allow us to preserve a form of Newton's second law in the rotational context. That is, net torque is equal to rotational inertia times angular acceleration. And after using this consideration to derive the rotational inertia for a point mass, we introduced the technique for calculating the rotational inertias of extended objects by direct integration. In this lecture, we demonstrate a one-dimensional example, leaving the two-dimensional examples for another time. In the remainder of this lecture, we cover topics you need to know in order to answer the questions in this week's problem set. Rolling without slipping covers a very common constraint in problems involving rotational dynamics, and the analogy between translational dynamics and rotational dynamics cover many details and formulas we gloss over. And as we wrap up, we take a brief look at the cross-product definitions of rotational quantities, which allow us to handle quantities such as angular velocity and angular momentum as fully three-dimensional vectors, not just limited to describing them as clockwise or counterclockwise. There are many more examples and demos I would like to cover, and did cover at some point, then we can cover in this brief 2-hour video. So please look for an optional third lecture video for this week for these additional examples, which are strictly necessary for you to be able to complete the homework problems.
So for the rest of today, we actually have to set aside some time talking about something called rotational inertia. And in keeping with the analogy that I've been trying to emphasize, what do you think rotational inertia is similar to? Like if you are trying to find the counterpart in translational motion. So, okay, inertia maybe. What is inertia? I don't think I really used the word that much before. I could have, but so, okay, you could say it's similar to inertia. Well, so inertia is actually synonym for a different word that we actually do use a lot. Friction? Not friction. You are thinking of inertia as something that stops something from moving. That's not what inertia is. Inertia is something like in everyday language, when we talk about inertia of a large organization, when it gets moving, it actually keeps on moving unless something happens to stop it. It's related to Newton's second law or first law or whatever. So if you're treating inertia as a noun that's referring to an object or property, it's a synonym for mass. Or you could say one of the properties of mass is inertia. The second property is the one that we haven't talked about yet, gravitational attraction thing. But so rotational inertia will be similar to mass that we talked about in translational motion. So hopefully we'll have some time to talk about this as well. All right, I really do have to go over this before we wrap up the class today. Otherwise, I've written this down and I've never actually finished what we are talking about here. So we spent some amount of time dealing with the torque. And in some future class, we'll deal with some problems that are like a standard strategy. As in you analyze the net torque, and that'll give you some angular acceleration. But as you try to do that, a piece of information you need to get is this quantity that's analogous to mass. And for now, I'll give you the symbol for it, and I'll give you its names. And we'll do a quick exercise that'll hopefully build some intuition for this quantity for you. So the letter we use for this is I. I guess I for inertia. But it's not, inertia, because if I just say inertia, that's mass. So it's not inertia that I'm talking about. It's a particular type of inertia. And I will have to tell you that there's two different names for it. They are both commonly used. The second one that I'll give you is a little bit more old-fashioned, but I think your textbook still uses it, so you have to know both. So the word I will use most often is this, rotational inertia. It's sort of what it sounds like. It's like inertia, but it matters for rotational motion, right? And the other name that's more old-fashioned, but your textbook, I think, uses it, is this name called moment of inertia. So inertia part is clear, what we mean by that. The whole moment thing, I have no idea. All I can tell you is that it has nothing to do with the time. It doesn't have anything to do with moment of time. It might have something to do, there's a sense of moment that means some kind of weight. There's when you do like electrostatics, there's something like multiple moments or like moment of, it's an old-fashioned term. But when someone says the word moment of inertia, it means the exactly same thing as rotational inertia, and it means what we are going to refer to with this letter I. So your lab today is actually a lot about rotational inertia. You're going to be measuring some amount of rotational inertia for something. The exercise I want you to end the class with, this used to be part of a lab that, we are not doing this semester. So this is what I want you to get. Let's see, I need to pass this out in an efficient way. Yeah, could you, let me do it this way. Could you take this, pass the rest back? Let me just get one for Tikal. You will need, for each desk, you will need one full ruler. And let me pass out these wooden rulers. So these are half meter sticks. For each desk, thank you, Kiranji. So for each desk, you will need 2 of these. And yeah, could you pass out the rest? Thank you. So you have maybe a couple minutes or so. In that time, this is the sense of rotational inertia that I want you to develop. So the rotational inertia, you can get a sense of it by taking this and trying to rotate it. And your your fist doing this versus actually rotating it, it does take more effort, right? Yes? Now, when you take this, when you take these 2 rulers, they have about the same mass, right? No, 2 rulers, 2 of them. Yeah. Okay. When you take 2 of them, then they have about the same mass. And I want you to try this and compare that with this. One should be easier than the other. Yeah? So, I want you to think about, why is it easier to rotate this than this? That's one I want you to think about. The other is even taking this same, 2 rulers, if you change the place where you are holding and do the same thing, it'll suddenly become harder. So, I want you to think about, why it's harder. So, oh wait, I have 2 minutes. Okay, I think I have, so, you can do that for the rest of the class, but let me just prepare you for the lab. So for the lab, just so you know, we don't have a formula for rotational inertia yet. But what you do have is you do have a role for the rotational inertia. So here's one role rotational inertia fills. So this is the Newton's second law equation, where this rotational inertia plays the same role that mass plays role. Do you know of any other formulas where mass plays a role? Give me some of the formulas where you see mass in it. Well, we already have that. Momentum, okay, we'll come to that. Some other formula that has mass in it. Kinetic energy. So I want you to, because that's what we are going to use for your lab. So you don't know anything about anything else about rotational inertia yet, except that it's similar to mass. Well, here's a place where mass has a role. Kinetic energy is given by 1/2 times mass times velocity squared. And I'm going to sort of trust this picture that I have been building, that there's a relationship between these two, there's an analogy between them. So trusting in that analogy, I have more reason to trust in that you guys do. I'm going to guess at this formula for rotational kinetic energy. That rotational kinetic energy is given by 1/2 times something that's analogous to mass, so rotational inertia, times something that's analogous to velocity, or angular velocity, n squared. So this is an expression formula that you are going to take as given for your lab. So starting with this, you are going to make some measurements, and using those measurements, calculate rotational inertia, and from the rotational inertia, see, how rotational inertia might depend on other quantities. I have a sense it should depend on mass, but as you saw with the ruler, it's going to depend on some other quantities. And in your lab, you will measure that quantitatively using some specially made apparatus. Let me pick up from where we left last time. So where we left last time was with rotational inertia. You guys did that quick demo with just shaking this around. And so you got some sense that rotational inertia depends not only just the mass, how heavy something is, or how much material there is, but also the size of the object. Because when you did this versus this was harder. Even though in terms of material, there's the exact same amount of material in the 2 half rulers, 2 half-meter sticks as in 1 meter stick. And in the lab, you saw that rotation, I put away all the, but you guys remember the device that you are using, right? The rotational inertia of that rotating object, it depended on where you place the mass. And what you should have seen then is that rotational inertia goes roughly proportional to some kind of size squared. That's what I was hoping you would see in the lab result. Yes? No? That sounds kind of familiar? Yeah. Yes? Okay, so what I want to do in the lecture today is actually derive some formulas for rotational inertia. We'll start out with the most basic object. And so the thing about rotational inertia is that it's going to get complicated. In fact, it's the first quantity where there's a whole table of formulas, and I'm not expecting you to have them memorized. I do want you to know some key ones, but I'm not expecting you to have this, 7 or 8 things that are listed here. So let me start out with a very basic portion of the rotational inertia. So all of this is motivated by trying to hold this relationship true. Let me copy it here. So all of this is motivated by trying to have a form of Newton's second law, except that it applies in the rotational case. That net torque is equal to rotational inertia times angular acceleration. And from last class, we know how all of these are defined, right? With the net torque, we know how to calculate torque from force. Torque was calculated as force times some distance times sine theta, the angle between force and the displacement vector. And you guys know the angular acceleration. This would be, to relate it to the translational quantity, it would be the acceleration, or more precisely the tangential acceleration, divided by the radius of the circle that it's going, right? And what we didn't quite finish covering last time was this quantity, the thing that we call rotational inertia. And this is actually how we are going to derive rotational inertia. You can actually derive rotational inertia even for the very basic scenario. So what's in problem 5 of your worksheet 11 is the very basic scenario. Rotational inertia over point mass. What is the rotational inertia of this point mass about a particular point? So we are going to so I guess you could call it derivation or definition, but we are going to fix it in such a way that this equation is true. So this equation is true not by accident. We make it true on purpose. So we define rotational inertia in such a way that this equation is made to be true. So let's do that. It hopefully won't take too long. And once we have the basic relationship, then we can use that to derive more complicated ones, like the rotational inertia of a rod about its center of mass or about its end point. And I'll try to do maybe 2 examples. Okay, so let me just follow through problem 5, since that kind of sketches out what I need to do. So worksheet 11, problem 5. So this is the setup that's there. You have to imagine a point mass. So you could imagine the point mass as maybe this thing, because it's easier to make this go in a circle. So you have to imagine a point mass. Imagine you are looking at this from above, and you are somehow pushing it with a force to make it go in a circle. So imagine a point mass that's made to go in a circle like this. So imagining that from the top view, what it would look like is I have a point mass of mass m here, and it's going to go in a circle of radius r. So something will cause this mass to follow this circular path. In the example that you have seen before of conical pendulum, that something will be string. But whatever that it is, I don't really care what that something is that's keeping it in a circle. Because right now, would you say that this tension is providing any torque on this mass about an axis that's going through my hand, vertical axis? Is it providing any torque? No, right? Because you see that because it's rotating at a constant rate. So nothing is causing it to change its rotational state. Yeah? So as I look at this mass, so whatever is keeping in a circle, I'm going to ignore it for angular acceleration. Now what I'm going to look at is, okay, let's say this starts out at rest, or it starts out not rotating. And if I want this to start rotating, how would I need to apply force? So the tension actually, so tension that's pointing to this point here, it will not cause it to rotate. If there was nothing but the tension here, this would just accelerate linearly towards the point where this is held. So how would I need to apply force in such a way that this starts rotating? Yeah, perpendicular to tangent is radial. So I think you mean along tangent, right? Yeah, let me just to clear up the vocabulary. So this mass is here. When you are imagining something that's circular, there are 2 words that we use to describe directions. One is radial. So this is the radial direction, because it's coming away from or going towards the center. That's the radial direction. And what we call tangential direction, we call it tangential because it's a tangent to the circle. So this is what we call tangential. So we need to apply a force. And the force would need to be applied in the tangential direction to cause this to rotate, right? Yes? Okay. Yeah, so let's start out with a description. We are going to apply a force. We are going to apply a force that's in a tangential direction. And this is going to cause this to angularly accelerate. There will be angular acceleration caused because this force produces a torque about this point here. Okay? So the Newton's second law equation in this scenario would look like this. Newton's second law. So we are going to define our quantities in such a way so that this relationship is true. That net torque is equal to rotational inertia times angular acceleration. Exactly what I said before. So I know how to calculate net torque due to this force here, right? So let me write it down. It doesn't seem all that hard. So net torque is just the torque due to this. There's nothing else that's causing a torque. So it'll be this force times this, this radius r, right? That's the displacement from my center of rotation. And what would the sine theta be in this case? 1, right? It's 90 degrees, so let me just write this as FR. All right, so I say that's equal to, and this rotational inertia is the quantity that we don't know. And that's the quantity that we are trying to define through this by enforcing this equality here. Yeah? So let's write down what angular acceleration is. Well, I didn't pick the colors well. Let me use orange for angular acceleration. Okay, angular acceleration, I want to write it down in terms of some linear quantities. So what linear quantities do I use? So angular acceleration is given by tangential acceleration. So if I want to make it clear, I'll write down tangential. Often I'll just skip it. Because if you're talking about rotational quantities, tangential is implied. Divided by the radius of the circle. Okay. So, so far we haven't done nothing but definition. So this is how torque is defined, or the relationship of torque to the force is defined. This is how relationship of angular acceleration to acceleration is defined. Okay? So once we have this written down, then we can try to figure out, okay, what should rotational inertia be? Right? So I'm going to just solve it algebraically. Let's just solve for it and see what we get. So rotation inertia I, just moving everything over, I get it's F times, or force times the radius divided by the tangential acceleration, and radius goes on the numerator, so I'm just going to write it as squared. Now, I don't really want to leave this in this form, because this seems to say that rotational inertia, as in how difficult it is to rotate this, depends on acceleration. And that doesn't feel right to me. In fact, if it says it depends on force, that also doesn't feel right to me, right? Because whatever the rotational inertia is, it should be the property of the object. And the force and acceleration are dynamical quantities. So what would I do to get rid of force and acceleration? Asia? Yeah. So you use Newton's second law. So recall from the Newton's second law for translation, we said the net force is equal to mass times acceleration. Here, in the tangential direction, this is the only force. So we can say, well, this tangential force should be equal to mass times the tangential acceleration. So when you write that out, this is what you get. Mass times tangential acceleration times r squared over tangential acceleration. Tangential acceleration cancels out. So the whole reason you would do this substitution is with the hope that this would cancel out. So that you end up with rotational inertia is equal to mass times r squared. And you can actually take this as definition. So this is the rotational inertia of a point mass. So if you take this as definition, that would be fine. This is an expression that will never be wrong, as long as you're talking about a point mass. So if I'm talking about rotational inertia of this point mass, or a mass that's small enough that I can treat it as if it's at a single point, as it's rotating around this circle, I can say its rotational inertia is given by however much mass it has, And the, let me have you make it easier for you to imagine the circle. Circle that's given by the radius from here to the ruler. So as it's going around this way, the circle that's given by radius from here to the ruler, that the r squared will give you the rotational inertia of this rotating. Good. Does this match with your intuition? What you found with the ruler, like rotating this way versus rotating this way, that it was harder to rotate this, right? If something's farther away, greater r, then it should have higher rotation inertia. Yeah? Like, this is lifted from your textbook. It has, so for like 8 different geometries, there are, 8 different formulas like those. I don't remember doing this for mass. For mass, when we are talking about mass of an object, we had whatever object it was, we had its mass. We didn't worry about, is this object, a cylinder shaped, or is it looking like a disk, or is it a sphere? We didn't care about that. Why are there so many bunch of different formulas for different geometrical objects? As an example, why does it list 2 different formulas, one for a solid cylinder and one for a thin hoop or thin hoop? If you don't have an answer, that's okay. Let me pose you this question instead. So let me ask you this question. Rotational inertia of a rod. And I know you can just look it up on the other side of the column that's not being projected. But I want to show you how it can be derived. For many of the rotation inertias you might use for a problem, you are going to be looking it up. But I want you to know in principle how to actually derive the rotation inertia. Because the rotation inertias that you see here, it's not an experimental thing. It's something that can be theoretically calculated. And I want you to know the procedure for theoretically calculating it. So let's say somebody asked you, what is the rotational inertia of a rod over length L, being rotated by its end point? Good. Let me draw that figure here so I have something to look at. Let's say we have a rod of length L, and I'm choosing to rotate it by one of its end points. So this is my center of rotation, and I'm rotating it back and forth either way. Good? So suppose somebody asked you, what is the rotation inertia? How would you answer that? Or how would you try to answer it? Let me give you a hypothetical answer. Could you say that it's equal to, you would have to know the mass of the thing. So let me give you its mass. Let's say it's a rod of length L, mass M. Could you say that its rotational inertia is its mass times L squared? So why not? Ali, why were you shaking your head? Like, why would this be wrong?
Because L is the whole length, so I think ML is the square.
So you said L is the whole length, but like you wanted to do this? That doesn't have correct unit. Because the unit, so whatever rotational inertia you have, it'll always have this unit. I'm glad that this got brought up. So this formula gives you one thing for sure. It gives you the unit of rotational inertia. When you look at the unit of rotational inertia, it's going to be kilogram times meter squared. Mass times length squared. And when we do this correctly here, we will also get that unit. But I want to highlight something that Ali said, that L is the length of the whole ruler. Right? L is the length of the whole ruler. So that is a good place to start. Meaning, if you're trying to apply this formula is valid at a single point. This formula is valid for this point here. Is the ruler, all of the ruler at this point? No, right? Some of the rulers is actually at r equals 0. Some of the ruler is at r equals, L over 2. The ruler is spread out over the entire length of the ruler. So when we ask this question, you actually, so without calculus, you have no way of answering this. Because it comes down to this. It's the answer to this question is mass times some sense of distance squared. And the question that comes up that you have no answer to is, what is this distance? Am I going to plug in 0? Am I going to plug in L? Am I going to plug in L over 2? How many people think L over 2 might work? It's you have seen many situations where the center of mass actually worked, right? It works when we are trying to figure out where does force of gravity act. We can pretend that it's at the center of mass and it works out. I will tell you with the rotational inertia, this is one scenario where it doesn't work. You can actually see it here. So if a center of mass could be used to describe the whole object, this and this would have the same rotational inertia. Because their center of mass is same, right? But you know from experience that they have different rotational inertia. Yeah. So this is why I want you to take the time to go over this calculational technique. And in fact, this will be, in this class, even though, Math 3A covers some integrals, we don't do a lot of integrals in this class. You've seen me use integral once to derive a formula, the spring potential energy. This is actually one example that requires use of integral that I'm going to expect you to know how to do on an exam. So let me take the time to illustrate the setup and actually go through a calculation here. I'll do it for one more example so that you'll have seen it enough. So yeah, this is the problem, the difficulty that there's no single distance that we can plug in. And if we were taking a guess, we might have guessed the center of mass. Turns out in this problem, it doesn't work. It doesn't give you the correct answer. So we have to fall back on our default method. And I call it default, but you haven't seen this yet. So I should take a little more time to describe it. So this is something you are going to see illustrated more often in Physics 4B. That's why I'm taking time to go over this in more detail. So as I look at this ruler, what I am hoping is that this was a point mass. That all of this mass was at a single point. Because if that was the case, I know how to deal with it. So what I'm going to do is I'm going to take this ruler, break it down into smaller bits, in my imagination, not literally, so that I can deal with each small piece. So imagine me just dividing up this ruler into tiny little pieces. Into tiny little pieces. I won't draw you all. So into tiny little pieces. Let me just draw a piece here that I'm going to use for illustration purposes. But imagine breaking up into tiny little pieces. And what I can say to myself is that I don't know how to deal with the entire ruler, but I do know how to deal with this one little piece. If it's small enough, I can treat this one little piece like a point mass. Right? Let me introduce some new symbols that will be useful. So I'm going to call the mass of this tiny little piece dn. You might have seen this kind of notation in your calculus class before. This is sometimes called, I guess you could call it differential. But I think the term that I like better is infinitesimal. Infinitesimal mass. As in, this is some quantity that is related to the whole mass, but it's a very tiny, very small portion of that mass. Okay, so this is a portion of the ruler has this much mass, and it is at a distance. Let me label that distance x. It is at a distance x. Right? Do you know what the rotational inertia of this tiny piece of roller is? Do you have a formula for it?
Is it the mx squared?
Yeah, dmx squared. So now that it's something small enough to be treated like a point mass, I can use this relationship. I can say rotational inertia of this object is equal to the amount of mass it has times x squared. So let me use this notation. So I'm going to write down di, the infinitesimal rotational inertia, or very tiny portion of rotational inertia coming from this, is equal to the small amount of mass that's there times x squared, the distance squared. Yeah? This setup looks okay to everyone? Yeah. Now, having said all of this, this is not the question that was asked before, right? The question that was actually asked was, what was the rotational inertia, not what is the tiny portion of rotational inertia. So how do we go from here to here? Yeah, so this is the integral that you have to do. And conceptually, this is how I want you to think about it. I think, so for people who have this view of an integral as some kind of an abstract procedure, this is, I think, a better way of at least imagining it initially. So think of this infinitesimal mass as a small amount of mass delta m. Sorry, I'm using delta in a weird sense, but bear with me for a bit. And think of this infinitesimal rotational inertia as some small but finite amount of rotational inertia that you can attribute to this. So let's say small amount of rotational inertia is equal to this small amount of mass times x squared. And if you wanted the rotational inertia of the whole thing, what you would do is you would take this piece, you would take a piece next to it, you would take the piece next to it, and you would add them all up, right? So for the total rotational inertia, you would simply add up all these with the index going from, let me do the index in a different color. You would add this all up with the index going from 1 to n, where n is the total number of pieces you've broken it down to, and this index would specify, all right, how much mass is in each little piece, and what is the position of each little piece, right? And this would be an approximation. It would be an approximation of what the rotational inertia of the whole thing is. Because, well, each little piece here, it's still not a point mass. It's even when you break this down into 100 1 centimeter pieces, each 1 centimeter piece has an extent of 1 centimeter. It's still not a point mass. So what do you do that makes what you calculate an exact number instead of an approximation? So this is what we will end up calling integral. But how do you go from this summation to try to get something that will give you an exact result rather than an approximation? Recall to your calculus class. I don't remember. It depends on who you had as a calculus teacher. But yeah, what goes to infinity?
The number of n's.
Yeah, you let n go to infinity. So you take the limit as n goes to infinity, and what that means is each tiny piece gets infinitesimally small. That's what infinitesimal means. So you take this limit, and in your calculus class, this is what you covered as Riemann sum. Riemann sum was the approximation to an integral. And when you take the limit, that each small interval actually becomes infinitesimally small, that limit, this is the integral. All of this coming back to memory from your calculus class? Yes? No? Yeah, so the reason I'm bringing this up, even though I'm really not going to go through this every single time, having this image in your head is important for doing this very first step. This very first step of setting up this portion of the expression that we are going to write down. So, we know we are getting to an integral. So what I'm going to do as the next step from what we have written down here, well, I'm going to say, well, I'm going to integrate this over the entire rod. That's what I'm going to do. But I will tell you this. In physics, when you see integral in physics, the integral itself is not actually the difficult thing. You will see here, it's a simple polynomial integral. Someone who was about to fail calculus could do that. It's not a difficult integral. But what is difficult is actually setting this portion up. That's the thing that you may have never seen in your calculus class. That's the portion where you have to look at the setup and think of, all right, I don't know how to deal with the whole thing, but I'm going to pretend that I'm going to break it down into tiny little pieces, and I'm going to set up an expression that tells me how to deal with that tiny little piece, and then I'm going to integrate this integrand, this expression, to get me the full result in a completely accurate, non-approximation kind of way. Good? Okay, so that's going to be the answer to the original question. So for the total rotational inertia, so this would be the rotational inertia of the rod, that's going to be equal to this expression that we have set up. And I have to say, okay, I'm going to integrate this over the rod. So far this is all just a symbolic notation, just reminding me what I'm going to do. It's like, it's like if you write down to-do list for the day, that's sort of what this is. It's like to-do. I have to take this quantity and integrate over the rod. But your to-do list actually doesn't tell you how to do any of the stuff that's on your list, right? So I have to change this into an expression that where I can actually use the integral formulas that I remember from calculus and use it. So when I look at this, I guess the first thing to address is what does the integral over the rod means? So what would that look like? Steven?
So it would be over the total distance of the rod.
Over the total distance of rod. Okay, I like that you are focusing on the distance. Yeah. So this is the reason I drew this one example piece. I had a parameter that was characterizing this piece. And that piece was this value x. Right? It's like trying to characterize people in this class by where you are sitting. Right? And if I want to add up everything over the class, maybe average your exam scores or whatever, then I'm going to have to add up for the student who is sitting over there, student who is sitting over here, and so on. So I'm going to have to add up x from all the way from x equals 0 to all the way to x equals L. Right? So let me do that. So that's one concrete thing I can do. Instead of saying integral over the rod, I can say, all right, my integral is going to go from x equals 0 to x equals L. These are my limits of integration. Yeah? Now, having decided on that, when I look at this integrand, I see that I have some problematic quantities. X, that's fine. I will figure out how to do that. This dm is a bit problematic. So it does indicate, how much mass is in this tiny little piece, but it's not indicated in a kind of in a form where I can integrate, because according to the limit I've set, my variable of integration is x. But this makes it look like my variable of integration is m, which is not even an actual variable. So this dm that we wrote down, it was a symbolic reminder to be re-expressed in terms of this coordinate variable x. So how would I do that? How would I express the small amount of mass here in terms of x, or something that's related to x? In other words, let's say I asked you, I have this ruler that's 100 centimeters long, and I want to have an expression for what is the amount of mass. So let's say this is 100 centimeters, 100 grams. I want to know the amount of mass in 1 centimeter of this ruler. Yes, Stephen?
I don't know how to answer that.
Yeah, well, whatever, if it's related.
So to find the mass of certain x, we know that for that small mass, if you multiply it by the total length, we'll get the total mass.
All right, let me write it down. We'll make some corrections, but so your idea is that small mass times the whole length. You want that to be the total mass, right? Something along that line, okay. I said the units here are not quite right, because this small amount of mass, it'll still be in kilograms. This is still kilograms. This is in meters. But this is the right general idea. As in, you can relate this whole thing to the whole length. So the first thing you kind of need to do is how to express the small amount of mass that's here in terms of, as a, I guess, a fraction of the total mass. Sergio?
So Dm times L equals M over L?
No. That still doesn't give me correct units. So let's go through this step by step. So let me just go through the example that I was going to go through. I mean, this is something that you already have an intuitive feel for. This is not a actually difficult question. You are just not used to dealing with it in a symbolic format. So let me give you numbers. 100 centimeter ruler, 100 grams. If I asked you what is the mass of a 1 centimeter portion of it, what would your answer be? 1 gram. Yeah, all of you know the answer to that. It's just that you are not used to expressing it in a symbolic format. So, well, 100 gram to 1 gram, 100 centimeters to 1 centimeter. That gives me some idea. I can express this as a ratio. So, okay, 100 grams, M, over the 1 gram that's in the small portion. So that ratio, I can say, all right, that's equal to the ratio of the lengths. The total length, 100 centimeter, L, divided by the small amount of length that's here. Yeah, so we don't have a symbol for that yet. Let me introduce a new symbol here. So this would be the symbol for what's the size of this. So this would be the infinitesimal dx. So L over dx. Good. So everyone thinks that this ratio sounds reasonable? Yes. Let me point out one thing. This ratio actually assumes one thing. It's kind of easier once I've written it out for dm. So let me do that. So let me solve this for dm. When you do that, you get this. You get the infinitesimal amount of mass. It's equal to the m over L, the total amount of mass divided by the total length, times the infinitesimal amount of length. And the reason I'm going through this circuitous route is because we haven't officially introduced this concept yet. This is what you might call density. If you have heard the word density, then that's what it is, mass per some spatial extent. Later, at the last week of this semester, we're going to actually do fluids and we'll do density properly. Here, it's like a linear density of the ruler. You take the however much mass of the ruler you have, divided by its length, you get the linear density. And what this expression here is assuming is that the density of the ruler is uniform. That one end of the ruler isn't heavier than the other end of the ruler. So you have a uniform density of ruler. Okay? So that's the expression we are going to use. And as long as this ruler is uniform, all of this, it will be fine. Now, what I'll tell you is that the problem that you will be asked to do on the exam, the density of the ruler will not be uniform. And so there you have to take on, so the symbol that we use for density, it's lambda. That's the symbol that we use for density. And in the exam, what you will have to deal with is where you have to write down the mass of the infinitesimal piece as the density times the length. That's what you will have to do on the exam. And this is how I make sure that there will be no memorized formula that you can use for that exam problem. You actually have to know how to go through this calculation step and actually do the unique calculation for the exam. Like if you're just trying to memorize this, I'm actually going to give you this shit for the exam. And there will be not a single formula here that will answer that particular exam question. So let's wrap up here. So I'm going to use this expression to plug it in here. So let's do that. I don't think I need the thing on the bottom, so let me erase this. So I have space for it. All right. And so the next set of expression will look like integral is with respect to x, going from 0 to L. So after I plug this in there, the integral will be with respect to x, which is good. That's how I was planning on doing it. dx times, now what I'm integrating is m over L times x squared. M over L times x squared. M and L are constants. I can pull them out. Everyone here knows how to do this integral? There's x cubed. What else?
1/3.
Yeah, 1/3. So m over L, factor dot, m over L. And the antiderivative of x squared, as Steven said, is 1/3 x cubed. And to evaluate this definite integral, you evaluate it at the lower limit and the upper limit. It's actually upper limit minus the lower limit. Right? I'm not using any novel notation here. This is something you have all seen in calculus class. Right? Yes, Ali? Yeah. So let me plug this. When I plug in 0, I get 0. So I'm just going to get what I get with the L. So here I'm going to get m over L times 1/3 L cubed. So this L will cancel out one factor there. So you will end up with 1/3 mL squared. So this is the rotational inertia of the rod when it's spun about the end, about one of the two end points. And this is one of the formulas that you would see in this formula sheet. So when I go here, long uniform rod. Oh wait, this is through the center. So here it is, long uniform rod rotated about the end. So 1/3 mL squared. That's exactly what we derived. Okay? So the procedure that you described here is how you'd go through it.
So let me set up something that looks like this, and then talk through the things about the rolling without sleeping that we need to that I feel like I need to lecture on. So it would look something like. I'm actually going to glue this to the ground so that it doesn't move when the simulation runs. Since this is simulation, I think I can illustrate this the idea of rolling without sleeping better this way. So imagine that you have some disk wheel thingy. When I start running the simulation, it's going to drop a very small distance, and then it'll hopefully just start rolling. That's a kind of normal thing that you are used to seeing. So let me do that. I'm just going to run the simulation. Yeah, and it rolls down the incline. That's kind of what round shaped things do when you set them on something like this. Now, what I want to highlight is things that things that I tell you to neglect as much as you can, whenever you can. Friction. So this simulation by default sets up kind of a reasonable friction coefficient. So the way this was set up, it started out with some amount of friction. So let's imagine what this picture would have looked like if there actually was no friction, if friction was truly negligible in this interaction. Let's watch what happens. And this is quite unusual setup. It's just sliding down without rolling. And in many physically reasonable scenarios, we wouldn't be asking you about sliding without rolling. It's more common for us to ask you about rolling without slipping condition. We might give you a question like, so you have a ball that's at on top of an incline, you let go, and it starts to roll without slipping. Or there might be some, or I guess sometimes we might not even say without slipping, it just rolls. And oftentimes we would be assuming that it doesn't slip. And in questions like that, unless you know what exact condition to use, it can be difficult because it will feel like you have a missing bit of information. You will have either used your conservation law or Newton's law analysis, and you'll have set up everything. And then when you're trying to solve, you have more unknowns than equations. So you can't quite solve it. And that would be because you are indeed missing a piece of information. And let me just write out what that piece of information that you are missing often will be. When you fully understand the rolling without slipping condition, and what this condition amounts to is it is giving you license to use this particular set of formulas. And depending on your situation, depending on what equations you're setting up, it might be one set of relationships versus the other set that's more useful, but they are all kind of interrelated to each other. And the relationships will be this. If you are looking at something like a distance rolled, then distance rolled, you can relate it this way. So if this round thing has radius r, the distance rolled would be the radius of the round thing times the angle theta, or the amount of the angle, the angular displacement it has undergone. So that's one relationship that might be useful. Or if you have something like a speed of the center of mass, if you have some translational speed of the body, then you can relate that translational speed of the body to the angular speed of the body. And that relationship would be the radius of the object times angular velocity of the object. And last relationship that might be useful is if you somehow know or have an expression for the linear acceleration of the body, acceleration of the center of mass of the body, then you can relate the acceleration of center of mass to the radius of the around the object times the angular acceleration of the body. And I hope you see the relationship between each of these three expressions. The relationship here is derivative. So if you take the this relationship, for example, x is equal to r theta, then you imagine taking the time derivative of this equation, left hand, right hand side. Then left hand side, time derivative of x gives you speed. And on the right hand side, r is a constant parameter. And so it just passes through the derivative. And when you have the time derivative of the angular displacement, that is the angular velocity. And when you take the time derivative of this expression, that's what gets you to the next expression. Derivative of velocity is acceleration. Derivative of angular velocity is angular acceleration. And so if you are able to justify any one of these expressions based on a good physical description of rolling without slipping, then you can get to any other two from having justified the one of the three expressions. So let me try to give a justification of why the rolling without slipping condition gives you license to use any one of these three relationships. It has to do with, let me see if I can demonstrate it this way. I think, I don't think it really comes through all that well in the simulation itself. So, so I would have to ask you to imagine. So imagine looking at this point here. You are looking at this point here, and consider these 3 points. This point where the ball is touching the surface below, this point in the middle, which might even be called the center of mass for uniform object like this, and this point up here, that's I don't know, 0.3. These 3 points are moving at different speeds. Right now at the very beginning, they are all not moving, so it's not very good. So let me do this. I'm going to let the simulation run for a little bit and then stop. So let me let the simulation run for a bit. That is, okay. I need to do this with a slower speed so that I can stop it at the right point. I want to stop it when that just barely touches the. Okay, there. Okay, so let me move these labels over. So at this point now, the disk has a speed. So it is rolling with some speed, and that speed that we would normally identify with would be this speed of the center of mass. So how fast this point is moving. It's moving, it has some speed. And what I want you to think about and consider is how the speeds here and the speeds here are different from speed of the center of mass. And really the most important point is here. This is the point. When we say something is rolling without slipping, it must mean that this point here, it's not sliding. Because if this point is sliding either way, then it's slipping. So when someone says something is rolling or rolling without slipping, they are in kind of in many words, they are giving you this information that this point has velocity of 0. And when you have that, then you can imagine. So this disk is it has a rather complicated motion. It's both translating and rotating. It's doing both at the same time. So while its center of mass is moving at this speed, it's also angularly moving. It has some angular velocity. So with this constraint in mind, the center of mass is moving at some speed of center of mass, and this point is not moving, its velocity is 0. I want you to try to imagine coming up with a relationship between this angular velocity and this speed of center of mass. And this is where a good understanding of how we define angles is really useful. So because we have a really special non-arbitrary unit of angle. I don't mean degrees. Degrees are totally arbitrary. In fact, the word degree is a shorthand for this is an arbitrary unit system. That's why we are saying degree. It applies to degrees, 360 degrees. It applies to degrees Celsius. It's totally arbitrary. It applies to degrees Fahrenheit. Totally arbitrary. With the Kelvin, you don't say degrees because it's not arbitrary. So when you have, I'm trying to draw a unit circle here. So to illustrate our non-arbitrary angular measure. So this is something that you cover in geometry class, but I find that a lot of students forget, or maybe you are never told this. Different people have different geometry teachers. So you are used to, so let's say you have something quite common and recognizable, like 90 degrees. And maybe you remember enough of radians to know that if someone asks you, oh, what is this angle in radians? Then you know enough to say, oh, that's a pi over 2 radians. But suppose someone asks you, why? Why is it pi over 2 radian? Then sometimes I get this answer, oh, it's pi over 2 radian because 180 degree is equal to pi radian. Okay, but again, I would ask you the question, why? Because with the degrees, it is an arbitrary unit. There's no reason or why. There's no reason or why one full circle is 360 degrees. It just is. I usually blame Babylonians, but maybe. Anyways, so with a unit system like degrees, I don't ask you why this is 90 degrees. It just is. But with radian, because it is a non-arbitrary unit, there is an explanation. There is an explanation why this is pi over 2 radian and not pi radian. We can just double this and have everyone in the world agree that this shall forever now be known as pi radian and the full circle will be 4 pi radian. That doesn't work because that goes against the rationale and logic of the definition of radian. And this is how radian is defined. Radian can be defined using a unit circle, or it can be defined using a circle of radius r. And radian is a way to measure angle by measuring distance. Because distance measurements are not arbitrary. Distance, you have physical object, you can put a ruler to it and measure distance. It's not arbitrary. So radian is a angular unit system that's designed to measure how much this angle is by measuring distance. So in a circle, you think about what other quantity varies as you change this angle. And some observant person thought through this and realized, the arc length changes. And in fact, how long an arc length is, it seems to be proportional to this angle. So we can define this angle by doing this. We can take the arc length and now everywhere except for the unit circle, you can't just say the arc length is the angular measure because you could also have a bigger circle. So if you have a bigger circle of radius 2r, then even though this is the same angle, this arc length is now longer. So you can't just take the arc length, but if you take the arc length and divide it by r, this is a quantity that only depends on how large this angle is and no other parameters. If we have a larger circle, both the arc length and radius will increase by the same factors, so that those same factors will cancel out. So this ratio of the lengths, that's how unit of radian is defined. It uses this ratio of two lengths to define this angle. And that's why one full circle is 2 pi radian, because the circumference of a circle is 2 pi r. So when you take 2 pi r, divide out r, you get 2 pi. And so until we change the definition of pi, the one full circle has to be 2 pi. It can't be any other value. And so radian is actually, because it's defined this way, it's not a real unit. As in, you can, when you see it in your system of units, like, omega, sometimes we call it radians per second. But from time to time, you might see people referring to unit of omega as being just inverse a second. And they are both right. It's because the radian is not a real unit. It's just the ratio of lengths. It's a unitless quantity. We say the word radian when we want to remind ourselves, other people, that we are measuring an angular quantity with that unitless number. But that unitless unit of radian is defined through this ratio in a very non-arbitrary way. Now, when you realize all this, then you can see that there's a really tight connection between the angle and the arc length. This arc length here, as long as you specify your angle in radian, the arc length will be the angle times the radius. So in this context here, what we would mean is, so if we want this point not to move, then as this moves at VCM, this would have to rotate at angular velocity that matches this relationship. The radius times the angular velocity would have to match the center of mass. So that in some amount of time, in the time that it takes this point to move a little bit, it'll also rotate by the right amount of theta, so that this point doesn't move. And once you figure out that much, that velocity here is 0, according to this, at this point it moves at VCM. At this top point, it moves at exactly 2 VCM. So that's the geometry that you have when you have a rolling without slipping condition. And here, when I let the simulation run, you kind of see that. Let me try to make it run even slower. As it rolls without slipping, you see, okay, so this point hasn't moved at all. This point moved a little bit. That's kind of matches r times theta, whatever this theta is. And then the point at the top, it's moved the most. So I guess I've just, without warning, I've shifted my point of rotation reference to down here, so that this is at r, this is at 2r, and given the same angular change, this is moved some arc length, and this moves some double that arc length. So, but this point of contact that doesn't move, it keeps shifting. That's how it does roll and actually does move. But wherever it happens to be touching, at that point, at that moment, its instantaneous velocity is 0. It's not moving. That's what rolling without slipping means.
So this is something called a rotational analog. I've been hinting at it since the beginning, but let me make it explicit this time. And this is really the reason I want you to start paying attention to this from the beginning. Because if you treat rotation as a separate subject from what you have been doing so far, it's just way too much information. There's no way I can memorize all that. But if you recognize the relationship between translational motion and dynamics to the rotational motion and dynamics, then there's not a single thing you'll have to memorize new. Everything that you saw in translation will just, by analogy, be transferred over to rotation. So let me write out this table for rotational analogs. So I guess, let me write down, rotational analogs. So, analogs as in analogy. So let me write down a few basic quantities. So the reason we can do this now is we just finished covering rotational inertia. This is the last of the basic quantities that have to be defined, so that any other quantity you can imagine in translation, you can essentially guess a formula in the rotational case. So in translation, we have the kinematical quantities: position, velocity, and acceleration. And we had, okay, so these describe motion. And we had a question of, okay, what causes motion? And what causes motion is force, right? And as you are introducing force, you actually have to define mass as well. You have to define inertia, because force is not equal to acceleration, it's only proportional. And the constant of proportionality is mass. That, all these quantities sound familiar? So I'm grouping them by, when we introduce them. So this covers all the basic quantities. And they directly correspond one-to-one to the rotational quantities. So there's the angular position, angular velocity, and angular acceleration, right? The rotational kinematics. And in the question of what causes rotational kinematics, what causes angular acceleration, our answer was torque. And as you introduce torque, you have to have a quantity that's similar to mass. And that's what we just finished introducing, rotational inertia. So that's the analogy, as in you can, anything, so let me just draw the line of analogy. Anything that involved position, if we are thinking about the rotational cases, you can express it in a way that involves angle. So, if I'm talking about position of this, let's say distance, that this ball travels from here to over here, then I can express it as, all right, the radius times the angular position, right? So I can say this distance here is some r times the angular position, or invert that relationship and say this is x over r. So I won't write down all of them since I already did. So there's the one-to-one sort of analogy between every quantity here and every quantity here. Let me write it down for force and torque. So we don't actually describe force in terms of torque. That kind of seems backward. Force is the basic quantity. And from force, we can write down torque is force times some displacement, or r, that's the radius of the circle that you imagine the point to be moving in, times sine theta. Okay? Same thing, we don't really describe mass from inertia, but we can describe inertia from mass. And as we just covered here, actual formula is not, so it now starts to get more interesting, because inertia is not just going to be simply mass times some distance. It'll depend on geometry. So what I can say is that rotational inertia of a point mass, at least, will be mass times the radius squared. Okay? And what I want to remind you is that when we came up with this description of rotational inertia, we had a particular goal in mind. We wanted to make sure that this relationship held, that net torque is equal to rotational inertia times angular acceleration. And this expression is true, whether you describe it using this or whether you describe it using this. That's by design. And having designed things this way means now we have an analogous relationship from what you have on the right-hand side, the translational quantities, to a similar quantity that would be on the left-hand side. So, after we've done all this, what are some of the derived quantities that we defined after we finished with standard strategy? What did we cover? We defined the work. So we said the work is force times distance. Okay, any other quantities? Energy. We have a bunch of formulas for energy. I guess let me not do potential energy because that's all translational. I can do kinetic energy. So kinetic energy is equal to 1/2 mv squared. All right, any other quantity we defined? We defined the momentum. We said momentum is given by mass times velocity. Is that it? Yeah, we had the impulse, but I'm not as fond of impulse as all the other things. Work is necessary because energy doesn't have a definition. Work is how you describe energy. But I have a definition for momentum. I don't really need impulse. So anyways, okay, I think that's actually it, right? So we have these three derived quantities, the quantities that are derived from these basic quantities introduced. And what I'm telling you, what I'm claiming, and you can, this is true, is that for the rotational equivalence here, I don't have to derive these formulas from scratch. I can simply look at the formulas here, copy it over here, just converting each of these quantities into their rotational counterpart. So for example, let's say I want you to figure out how much work am I doing as I try to rotate this from this vertical position up to this position. Let's say I want you to figure out how much work I'm doing there. Then looking at this expression here, I would guess, all right, work I'm doing as I cause some rotational motion to happen, I'd say, force, so torque. Torque times displacement, so change in angle. So I would say that. Yeah. And by the way, this is one of the reasons sometimes people get confused with unit for torque. Unit for torque looks like a joule, unit for energy, because angle has no unit. But what I'll tell you is that torque is not given in joules. Joule is a unit of energy. Torque is always given in Newton times meter. We never express that as joule if I'm talking about torque. Okay, so that's work done when I'm causing some rotation to happen. Kinetic energy, so that's the translational kinetic energy. I can talk about rotational kinetic energy. That's a kinetic energy that this would have from rotation. Or sorry, it's harder to say. Here, so right now, it has to be in the air, so I'm going to throw it up. But ignoring this vertical motion, it has a kinetic energy from this rotation. Good. We'll have a demo that illustrates that. So the rotational kinetic energy is given by, all right, I see this formula here. Let me copy it over, converting each of the quantities to rotational version. What's the rotational version of 1/2? Still 1/2. It's a constant. Times m. So the mass is going to be rotational inertia. That's going to depend on what geometry you have. So let me just write it down as I. To fix down what it is, I have to know the geometry. Times v, so angular velocity squared. So this is the formula for rotational kinetic energy. And because we went through this trouble, this is, by design, this is guaranteed to be correct. And let me finish this up here with what we are going to call angular momentum. So let me just quickly write it down. Angular momentum, we use the letter L for some reason. And we are going to describe this angular momentum in a more fundamental way on Thursday. But let me write down another version that's based on this. So momentum is mass times velocity. So I might say angular momentum. Let's say I think it might be rotation inertia times angular velocity. And this is pretty close to true. It's true almost all the time. There are some exceptions that you can come up with, but that's what we'll talk about on Thursday. Good? Yeah?
I have a question about the work rotation is equals to torque times the angle, right?
Yeah?
But torque already has an angle, so.
Oh, yeah. I would have to be careful. So, let me not use theta here. Let me use phi. So, when you talk about the angle in torque, it's the angle between this displacement here and the force that I'm applying, right? So imagine I'm bringing this up from this position by applying a totally vertical force. Then yes, this theta will be changing as it goes from here to, so from something that's close to 0 degrees to something that's close to 90 degrees. Wait, that's very confusing. Yeah, but the angle that I'm talking about here, it's the change in angle here. So actually, I can imagine applying torque differently. Instead of applying a force here, I can apply torque near the axle. I can apply torque this way. So, in this expression, you don't even have an actual discretion of torque based on force. I would simply give you what the torque is to bring it up to here. And that torque times this delta phi would give you the amount of work you had to do. Yeah, so when you get into actually angular quantities, you do have to be careful because there are different things that can be rotating. So you have to be careful not to use the same symbol for different angular quantities. So I guess, I'm sorry, the way I should have really done is I should have changed this theta with a phi. Because this theta is same theta as this one. But this phi is something that's defined in this specific context. Good? Yes? Yeah. It's like, if you have two different people named Andrew, it's not a guarantee that they are the same Andrews. So usually you try to call people by different names so that you don't get confused. Okay? So this is the rotational analog. One thing that this is very useful is, it's useful in two ways. One, it saves you the trouble of memorizing all these new formulas. Because if you had kinetic energy, translational kinetic energy memorized, then, well, this is the rotational kinetic energy. You don't have to memorize anything other than this correspondence here. So it's useful in that way. And two, this analogy transfers over for your intuition as well. As in, whatever intuition you had for energy, rotational energy is still energy. So, you have intuition that energy is conserved. Well, rotational kinetic energy is also conserved. You can turn rotational kinetic energy into other forms of energy. And you might have some intuition for momentum. And that transfers over to angular momentum also. So I guess that's where I want you to do a couple of demos so that I can illustrate some of that intuition you might have. Let me do a demo for rotational kinetic energy. Or this is a demo where the explanation of the demo would be possible with rotational kinetic energy. I'm just using this as a paperweight or bookstop or whatever. So let me set up an incline. There's a reason that this has been sitting here whole semester. We use this for some things. So here's my inclined table. And what I am going to do after moving things that break out of the way is I'm going to roll down these two objects, a ring and a disk. And they actually do have roughly the same mass. So let's say they have the same mass. Turns out whether they actually do have the same mass or not doesn't matter, but let's say they have the same mass so that you don't have things to worry about. So I have two objects, disk and a ring of the same mass. And this is the question. When I roll them down, starting from the same height, let me stop them with this. So I'm going to roll them down, starting from the same height, and they're going to roll to the bottom. So the question is, well, do they reach the bottom at the same time? Does one reach the bottom faster than the other one? What do you think will happen here? They have the same mass. I mean, it doesn't actually matter because if I, imagine with the gravity, if I drop it, whether they have same mass or not, they'll drop at the same rate, right? So, but that's why I don't want to get confused by it. But let's say they have the same mass. But whether they do or not, it doesn't actually matter. Yeah, Sergio?
Copper one, the ring will reach the bottom faster just because of where the mass is.
Okay, so you are looking at how the mass is differently distributed, right? So I do want you to pay attention to that. So with this copper ring, the mass is farther outside. So I'm going to relate that to rotation. So in terms of rotational inertia, which of these two has greater rotational inertia? The ring, right? Yeah, larger radius for all of its mass. In fact, do you have a guess for what the formula for rotational inertia of a ring is? If I'm rotating it about by its center? Yeah, mr squared. So this is one example where actually all the masses are at the same distance. So you can just use the same formula as the formula for the point mass. It turns out, this turns out to work for a ring as well, as long as you're doing it about its center. So this is mr squared, and the rotational inertia of a disk is actually half mr squared. So, but you already have an intuition that this does have a smaller rotational inertia. So starting from that, this is what I want you to reason through first. Okay, so the ring has larger rotational inertia. All right. So this is how you'd analyze it using conservation of energy. Do they start out with the same amount of energy here? Yes, they start out with zero kinetic energy whatsoever and some amount of potential energy. So the second question, when they come down here, they have both zero potential energy. Will they both have the same amount of energy when they come down here? Let me restate the question. They started out with the same amount of potential energy here. After they roll down, when they are here, do they have the same energy? Okay, why yes, Ranjit?
Have no more potential energies.
Okay, no more potential energy, but I'm looking at the total energy. Do they have the same, Steven?
Assuming that is total energy is conserved, all potential energy turns to kinetic energy.
Yeah, so the key here is that, does this setup look like something that conserves total energy? As in, you don't have things sliding with the friction. Right? I mean, imagine a situation where you are rolling things down. Is that a situation where you look at it and say, oh, that conserves energy, right? I mean, that's the question you need to be asking. So since we introduced the conservation of energy and momentum, a lot of the questions, if you try to do it using standard strategy, it'll be too difficult. And you just won't have enough time to finish that on an exam. So the question you have to be constantly asking yourself is, in this setup, is energy conserved, is momentum conserved? And that's the question you should be constantly asking and constantly answering. I'm not saying the answer is always yes. Sometimes the answer is no. In that case, you have to do the harder way. But the question you should have been asking yourself from the first time you saw this was, is energy conserved in this setup? And go through the arguments you need to convince yourself that energy is conserved here. So energy is conserved in this setup. That's why when they roll down to the bottom here, they will have the same energy. They started out with the same energy. When they end up here, there's no reason for their energies to be different. Now, here's the situation you need to consider. When they reach the bottom here, not all of their energy will be in something we call translational kinetic energy. So translational kinetic energy is what you have been seeing so far. We haven't called it that because everything was translational. So there's a reason we've been using this cart and not these balls. This cart illustrates something that has translational kinetic energy and zero rotational kinetic energy. Because as it moves, everything is translating. And I mean, these wheels are rotating, but they are so tiny that there's very little mass and energy associated with it. Once you are looking at things that roll, it changes. As it rolls, a significant amount of its energy will be in rotational kinetic energy. Okay? So I'm trying to wrap up this end here. All right, so these are some of the facts that you need to put in consideration. They have different rotational inertia. This has greater rotational inertia. They have the same amount of total energy, both here and here. But at the bottom here, one of them will have greater amount of rotational kinetic energy. Which of the two do you think will have greater rotational kinetic energy? The ring, because you are looking at this. Well, if somehow omega doesn't change, then greater I would mean greater rotational kinetic energy. So let me flip the question around. When you look at the translational kinetic energy of both of them, which one do you think will have greater translational kinetic energy between them? The disk, right? Yeah, because this has to waste less energy it has to put less into the rotational form. So more of its total initial energy can go to translational kinetic energy. So that's the argument we are making. So the argument would be this should have greater speed by the time it reaches the bottom. Let's try it and see. I'll do it a few times. So let them roll down. Yeah, the disk does roll down faster. So let me do it a couple more times just to be sure. So yeah. So I swapped their position around so that in case anything that matter. Yeah. Sometimes the ring initially wins because it's a little bit distorted. It's not the exact circle. But over long enough of a roll so that you can average that over, you see the disk win over. So let me do it one last time. So ready, set, go. Yeah. The disk always rolls down here faster because it's its velocity when it reaches here is greater. So it's average velocity over the thing is greater. It takes less time. Yeah. So this is an illustration of kinetic energy or rotational kinetic energy. So by the time so they do it at different times, but when they reach the bottom here, they do have the same kinetic energy at the moment when they reach down here. But the difference is that the fraction of energy that's in rotational kinetic energy is greater for the ring than the disk. The kind of the downside of these physical demonstrations is there are always some physical imperfections. And here, one thing I will tell you, which you might have seen if you watch the video, is the ring is a little bit distorted. So depending on where it starts, sometimes it'll kind of be neck and neck with the disk. Sometimes it'll definitively lose, and it's not as repeatable as I'd like it to be, again because of the real world imperfections. So when you watch the demos, okay, here it definitely loses, and when you see it repeated a few other times, sometimes you will see it be more of a neck and neck. So one thing that I think so I wanted to do was redo this in simulation, because simulated world is a perfect world. It's one where we can change the parameters, we can get rid of certain things, and so I wanted to redo this in simulation and kind of explore some things that's hard to explore in a physical demo. So I just built this. This is so these are all glued to the background so that they won't move. The spheres, they are not glued, and they've been given properties so that they won't bounce around. There's still some friction so that when I let the simulation run, it'll roll, not slide. So okay, these two identical objects, they roll together kind of at the same rate. All right, that's good. So let me first start by replicating what we've done in the physical demo. So I'm going to replace one of these with the ring shape instead of the disk kind of distribution. Good. Okay, so I cut it, and I think doing that got rid of the. Let me do this thing because I do kind of need some marker to tell me if it's rotating or not. So I'm going to make my own marker that tells me which point of the ring is where. So I'm gonna put this together, and just so that this doesn't affect anything, I'll make its mass really tiny, as small as they let me make it, and I'll combine these two masses together. Geometry actions, glue together. Okay. So, and let's see what happens. So when I let the simulation run, you see the disk is now rolling faster than this ring. And you might say, oh, but that's because the mass of the ring changed. This is not as, with this whole thing cut out, it's not as heavy as that. Now, if you're familiar with how things behave under gravitational force only, then that shouldn't matter, it should cancel out, but let's just make them actual same mass so that that's not a consideration anymore. I'm gonna just make both of them 1 kilogram in the simulation. Make this 1 kilogram. So if anything, this is actually slightly heavier with that little thing added of as tiny a mass I can make it. Now, when I let them roll, then the disk still wins. So the calculation you would do is you do the calculation of conservation of energy. So both of these start out with the same, now that the masses are the same, they start with the same gravitational potential energy.
or they undergo the same change in gravitational potential energy in this simulation. And that change in gravitational potential energy, because this is a setup that conserves energy, it'll go into other forms of energy. And the two forms of energy it goes to is translational kinetic energy and rotational kinetic energy. And given the same rate of rotation, this ring with a higher rotational inertia requires it takes a greater rotational kinetic energy to be doing the same rotation. So, for example, if I change the properties of these objects, so give them no friction, that'll make them slide rather than roll, then you will see that these two actually slide down at the same speed. So let them slide down. They slide down identically. They don't, it's any difference between these two comes from the rolling. So, and the exact friction coefficient value doesn't matter as long as it's high enough that it can roll without slipping. So, so when you do that analysis, set up your conservation of energy equation. This change in gravitational potential energy equal to this term for translational kinetic energy plus this term for rotational kinetic energy, and the difference between these two is what is I, the rotational inertia. And the thing with the greater rotational inertia, given the same change in height, will have the smaller angular velocity, which will also mean smaller translational speed through the rolling without slipping condition. So that's the simulation version of that demo that you saw physically. Now with the simulation, we can do other things. So if you've done that derivation that I described, you will have seen that the actual radius of the thing doesn't matter, because the radius cancels out in the derivation. So this could be a super tiny thing. And as long as I let me use the back of the two circular things as the reference point, and you will see that that the size doesn't matter. So so let me put it this way. So so the previous size. With this previous size, let me make sure that it has friction. Okay, so we'll do a quick measurement of how much they are far apart by the time the disk reaches this end. So let me mark the differences between the boxes this way. I can do it this way. So okay, that's kind of close enough. So I'm gonna have some error in where I stop it, but I think it's gonna be fine. It won't affect things too much. And in terms of measuring the difference in the edges, the way I can do it is I can take this and I can have this box start at the edge of the disk and end at the edge of the ring, at the far edge of the ring. Okay, I'll have this set aside so that I can refer to it later, and then we'll move this back. Move this back. Let me zero out the velocity here so that it doesn't have inherited velocity anymore. Let me make sure they don't have angular velocity. No angular velocity, and I think I have to make sure that this loses all its velocities. Oh, okay, it's lost it. Okay, let's double check that with nothing changed, that these two still reach the bottom the same way. Okay, yeah, and okay, measuring the ends, they kind of match. Good, good, good. So now I can just undo, and it'll start out at the same velocity, 0. And now I can change the parameters of this. So from the derivation, hopefully you have a sense that when you change the radius of this ring, that it's not really gonna affect anything. The amount by which this falls behind should still be exactly the same. So let's give that a try and see if simulation confirms that derivation result. So we'll let it run, and I'll try to stop it Okay. Oh, good, good. So that's the same point where I stopped it before, and measuring the distance doesn't quite work. um, if I had to guess, that mess might have played a little bit of role. So let me do it this way. Gonna undo, undo. So I'm gonna make the mass of this um, the same as the mass of the disk, mainly so that the relative mass between the ring and this little tiny thing is, small. And let's try running it again. And if it doesn't give me the result I'm looking for again, I'm just gonna have to. Oh yeah. So good. The far edges, they match up. So the amount by which this ring has fallen behind matches up exactly. So as long as that, so that tiny little piece that I attached to be able to tell when it's, when it's sliding, when it's rolling, that kind of acted like the defect in the physical setup that I was describing earlier. So we spent a lot of time trying to build intuition for rotational quantities. With the short time we have in this lecture, we won't be able to cover everything in detail. The good news is, almost everything you need to know in rotation, you have already learned when we were working with the translational motion and dynamics, as you saw with the analogy between translational motion and rotation. A lot of problem-solving approaches you learned earlier, such as Newton's law strategies and conservation law strategies, will continue to apply in the rotational context. For the many demos and examples I would like to show you that we don't have time for in this video, let me make a third optional lecture video for this week. This lecture video will be optional in that you can do all the homework questions without needing the content of this optional lecture video. For the topics you do need to know for the homework questions this week, let me first remind you of some definitions you have seen. You have seen the definitions of quantities in rotational kinematics, theta, omega, and alpha, for angular displacement, angular velocity, and angular acceleration, and how they are related to the tangential quantities. You have seen the definition of torque as displacement times force, and how this gives us the rotational version of Newton's second law, that net torque is equal to rotational inertia times angular acceleration. And we talked about rotational analogs, basically covering everything else we didn't cover in detail. Now, I need to tell you a little bit about the cross product and the cross product definition of the rotational quantities. This is an approach that allows treating rotational quantities as full three-dimensional vectors. Many of them we call them axial or pseudo vectors. For the homework, you need a definition of cross product and how to calculate it using vector components shown on screen right now. And next video will go in detail about working out the cross product using vector components. And the following are the definitions of rotational quantities using the cross product. Torque is r cross f. Angular velocity is based on r cross v divided by r squared to make the units come out right. Angular acceleration is based on r cross a, and angular position vector is based on r cross delta x. And for angular momentum, its definition is L is equal to r cross p, but often it'll be equal to rotational inertia times angular velocity in most situations in this class. Oh, and just as force was time derivative of momentum, torque is time derivative of angular momentum. I encourage you to look at the optional third video this week. And now, demonstration of cross product by components using one of the homework questions. So what it comes down to is you have to know how to do cross product using component notation. And I think the questions we are asking in this homework set, you don't necessarily have to do the full version, but I think being aware of the full version helps you. So let me start here. It says a particle of mass, some mass, has some position vector r at a particular instant of time
when its velocity is some value with respect to the origin. So let me just draw some figures so that I have something to visualize. So the particle is going to be in the quadrant 4 because it has positive x and negative y. It's somewhere over here, and it has positive x velocity. So it's moving in that direction with the speed of v. And this is my r. All right. So what you need to know is the formula for angular momentum to start, which is that the definition of angular momentum is the displacement, it's that exact r mathematically, cross product with the momentum. And you've seen this cross product in different ways. And the formula that I actually prefer is, and I even call it physics definition of cross product, is the one that's based on relative angles and magnitudes. One that says the magnitude of this whole thing is equal to the magnitude of r times magnitude of p times sine theta, where theta is the angle between them. That's the usual definition that we prefer. Now, applying this in this context will be tricky because, for one, you're not given this angle between these two things, or I guess more precisely, this angle here. You're not given that angle. If you want to work it out, it's going to be cumbersome. So really what you need to use here is the component definition of the cross product. And I think I have a lecture video showing it, but let me just do a quick version here so that I can show you how I memorize this. So the easiest way to memorize the component version of the cross product formula is to memorize this as a determinant of a 3x3 matrix. And this 3x3 matrix is formed in this way. So the 3x3 matrix that you use to memorize the component definition of cross product. The first, so you build it row by row. The first row has the unit vectors, x hat, y hat, z hat. The second row, and the order matters here, it has first of the two vectors. In this case, it's r. So I have x component of r, y component of r, z component of r. And the last row is the second vector. So I have x component of momentum, y component of momentum, and z component of momentum. So that's the matrix that once you've built it, that'll help you memorize the component definition of cross product. Because the way I memorize it is this L here. It's the is the determinant. I mean, in the algebraic sense of this 3x3 matrix. And if you remember your linear algebra or college algebra, I forget when you covered this, there's a kind of a mnemonic device for memorizing determinant. It only works for 3x3 matrix, and it goes this way. You kind of write two extra columns, or you copy over these first two columns so that you have x hat, rx, px, you have y hat, ry, py. And the way you memorize it is you can kind of build this word puzzle. You can build these diagonal combinations. Diagonal here. And so there's three diagonal combinations. And these ones that go diagonally downward to the right, they are associated. So they get multiplied together, and you associate positive sign with them. And these other ones, let me use purple, that goes diagonally to the left, or downward to the left. You also have three combinations here. They get a negative sign associated with them. So you have this whole complicated product we are building. So let me, as I'm building it, let me collect it by like terms. Let me collect it by terms that contain the same unit vector. So I know they go into the same component of this L vector. So L of X is going to come out of these two combinations, R plus Ry PG, Ry PG minus this combination here, RG PY, RG PY. And there are other kind of other patterns you can pick out here, cyclical, anti-cyclical permutation. Let me not get into that. I'm just going to use this mnemonic device to remember and write down the formula. So let me do the Y component. You'll just have to follow it with your eyes. So Y component, it's these two. Follow it with your eyes, not my highlighter. So the Y component of the angular momentum is RG PX, that's the positive part, minus the RX PG. And finally, the G component of angular momentum is going to be, let's see, so I'm looking at this, and I guess that actually contains both. So the positive one is one that's going to the right downward, so Rx Py minus Ry Px. Okay, so that's the full formula. And if you needed to find angular momentum in arbitrary direction, that's how you do it. Now, for these homework questions, you will see that I guess I don't know what the term is, product. No, the things that you are multiplying, they'll be given in such a way that the product is in a kind of one of the three axis directions. You can kind of see, imagine plugging in these numbers, and you will see that each of these end up just being 0. Because the momentum has no G component, so that's 0. Position has no G component, so that's again 0. Same thing in the Y component here. These 0 G components make this whole thing 0. So really the only non-zero component you have to deal with is this one. So you just plug in the numbers here. Plug in the number. You have the X component. You have the momentum doesn't have Y component. Okay, that makes it simpler. So this part is gone. So you have the Y component of momentum. Remember both minus signs, which will cancel out, I guess which will cancel out. So it's going to be 4 times momentum. So that's going to be 3, so mass times velocity. So 6 kilogram times 3 meters per second. 72 kilogram meters squared per second. Let's see if that's what we get. 72, maybe. I don't know. And you will see that when you look at the options. Oh, yes, and there could have been a lot more options. And it's going to be positive G. And you can actually see that it also matches with the right-hand rule, in that if you try to kind of put your right hand, you can do it yourself, but yeah, use the component definition. And you do the same thing with the force and torque. So you have to remember the definition of torque, which is that torque is defined as the displacement cross product with the force. So at this instant, really what matters is the displacement. So we are going to be using the same position vector here. And torque about the origin. So the force only has Y component. So I guess that's important, so that when you do R cross F, these are still going to be 0 because of the non-existent G component. And when you get to the G component here, so the G component of torque, it's going to be Rx Fy minus Ry Fx, and the non-existence X component of force makes this go away, so you're just dealing with this. So it's going to be 1.5 x component times the force 5. So that's 7.5 Newton meter. Let's see, 7.5, and it was positive, so it should be again positive z direction. Yeah, I guess negative wasn't an option anyway. So yeah, it's. I think there are a few questions like this on your this homework set that tells you to apply the component definition of cross product.